Hello, my name is Nigel Griffiths. I work in Advanced Technical Support, Power Systems, IBM Europe. In this Power 7 movie, we're going to be looking at active memory expansion. So how does AME sort of basically work so we get an understanding of what's going on? Well, here in my model we have a lot of memory pages sitting in memory. Of course, when the CPU comes along to access memory pages, a cache line is put into the processor, it makes changes, and eventually it's flushed back out to memory. We're going to allocate some of those memory pages into a RAM disk. This is a concept we've had for a while in AIX, where you can treat these pages of memory like a little disk, and we can actually then do things like paging them in and out of that disk space. Now that doesn't actually buy you anything. You have to be in the regular memory pages for the CPU to access, so that you can't actually directly access things in a RAM disk. So what's the point in saying that? Well, as we move things in and out of that RAM disk, we could compress them. Now in this case then, as we move it into the RAM disk, we compress it, make it a lot smaller, so we can save more memory pages in that RAM disk than we could otherwise. But when we actually want to access one of those memory pages, we can't access the compressed copy. We have to uncompress it and put it into a real memory page for the CPU to actually access. Now the point of this exercise is that it's a couple of thousand times faster to compress and move the memory into this sort of RAM disk than it would be to actually page the memory out to a real disk. Of course, disks are going, 10,000 times slower than we can access memory, even though we're doing this compression on the fly. Now be careful, this isn't exactly how it operates. Now when I've talked to the developers of AME, they said this is a good model for understanding what's going on. It's doing a whole lot of extra clever things as well. For example, there isn't this hard boundary between the memory pages and the RAM disk. They flexibly move this up and down as needed, as long as they're getting the expansion factor that they want, and depending on the compression ratio they're getting at the time. Okay, here's my AIX partition. I'll just check what AIX level it is. So it's AIX 6.1, Technology Level 4, Service Pack 2. That's the minimum requirement. If you haven't got that, you're not going to get AME working at all. Next thing to double check is we actually have this AME pat command. If you haven't got the pat command, then you know you haven't got the right copy of, or the latest version of AIX. So that's there. We'll come back to that later on. Something else we might want to check is, are we running in Power 7 mode? I'll use the lsconf command. That gives us a good summary of things. So it says here we have a Power 7 chip and it's in Power 7 mode. Here's my Power 7 server on the HMC, and we'll look up properties and capabilities. And I looked down this list and I thought, hang on, there's nothing about active memory expansion, but then I noticed there's a scroll bar here and we have active memory expansion capable true. Okay then, let's deselect that and we'll select our logical partition, configuration, profiles. I've got a profile here to force it into Power 6 mode. This is my normal profile. So I want to make sure that when this starts up we're in Power 7 mode. Then we'll look at the memory. We'll see down the bottom here active memory expansion. This would not be here if we didn't have the AME capable set for the machine. And yes, we'll click that. A factor of 1 to 10. 10 is extremely optimistic, and I doubt if we'll ever see that. I'm thinking of something like 1.1 to 1.5 as sort of the more usual level for expansion in practice. So we'll leave it at 1, which means it won't be trying to expand memory. At the moment, we can change that dynamically later on. Now our machine is actually running at the moment. The only way to get that activated is to actually shut down our copy of AIX, hard down, and then start it up from scratch so we pick up the new settings. Okay, and we're back up. When I first started using AME, I spent a couple of days learning a few things the hard way. I'll quickly go through these and perhaps save you some time. The first one was that I tried to use AME when there was free memory on the system. I had 1 GB of memory for the logical partition, but only about half of it was actually in use. You run this command called AMEPAT, and it gives you a little report about what it thinks is going on. And it very politely told me that actually there's free memory on the machine. It's not doing any compression at all because there's no need. You have free memory on the machine. And it politely points out that you could actually release half a gigabyte of memory here and it would make no difference to performance. So unless memory is under pressure, there's no real point of having AME. Next, I found and read the white paper. It's well written, highly recommended. And it says that AME doesn't compress pinned or file system cache pages. The reason for that is that you pin a page in memory because you want high-speed access to it, so it doesn't make sense to compress it. File system pages aren't cached because you can already do two things to free up those pages. If the copy in memory is the same as the copy on the disk, then we can just free up that page and put it on the free list and use it for something else. This is, if you like, a perfect compression algorithm from using 4K to absolutely nothing at all. If the memory copy of the page is being updated and needs to go to the disk, then it's better to actually do the paging right now. You don't really want to compress it, and when you need to page it out to the disk, then you have to uncompress it shortly afterwards to actually do the I/O to the disk. So what are the pages that AME is going to actually go and do the compression of? Well, that is the pages of memory that are inside programs. I then started my workload generator to actually make my machine busy and actually use up the memory. Each program allocates itself a big chunk of memory and then goes around touching pages inside that memory, much like as a real program does. I then used the AMEPAT command and it said we had a compression ratio of 7:1, which is, I know, completely impossible. So I had a quick look at my program and I said, okay, it's allocating memory pages. When memory gets into a program like that with the malloc command, it actually gets zero filled. This is part of the Unix operating system. We've been doing that for 30 years. It meant that all of the pages inside my program were completely full of zeros. And of course, when you compress a complete page of zeros, you only need a few bytes to actually compress it into. And that's not really like an application, is it? So my workload generator wasn't producing something like a real-world application. Well, you hope it doesn't. If you have programs that do things like allocating a 4K page and then just putting a few bytes up one end, AME will spot those pages and they'll be very good candidates for compression, and you may actually get high compression ratios for badly written programs like that. I guess most programs, though, you won't expect a ratio like that. I then changed my generator to put random bytes in all the pages. And then when I used AME, it said, I can't compress any of these things. If you have a page that's completely random, you can't actually compress it into less bits. So again, my generator wasn't like real life. So I had to make some more changes, and so it's random with some repeated data in it now. And now my program is behaving itself, and I get a ratio between 1 and 2. That's sort of where I'd expect most of the compression ratios to actually sit. Around the 1.5 to 2 times compression ratio. The next thing I noted is that in my small example here, I have 1 GB of memory. That's a very small logical partition. These days people are using, for one CPU or core, they're using 8 GB, 16 GB, maybe more memory per core. So this is a very small one, and I noticed that when AME is recommending that you could reduce the memory inside this logical partition, it does it in these 1/4 GB chunks, but when it gets down to 1/2 GB, it says that it's not sensible to go below that to run a copy of AIX. So when I get reports out, I don't have lots and lots of detailed different options of how to reduce my logical partition, simply because it can't actually take much memory out of my partition. If you had a partition with 64 gigabytes of memory, you'd get more interesting reports saying, well, if you took 1 gigabyte out, then AME would be using this much CPU, and if you took 2 gigabytes and 3 gigabytes and 4 gigabytes, then you get a more interesting report with more variations in. Let's use that AME pat command again, and we find actually you get a pretty nice summary of what's going on in here. It's a partition name, we're in Power 7 mode, we have 4 CPUs online, and we have SMT4. We actually have 1 gigabyte of real memory in here. Nice summary, enabled and uncapped. It's saying active memory sharing is disabled. Now, of course, you can use active memory sharing and active memory expansion. I recommend you get fully up to speed with them separately before you try them together. Together, there's 5 different sorts of paging, and it's going to be quite difficult to understand what's going on. And we can say that the target here is an expansion factor of 1, so we just get 1 gigabyte of memory. Then if we continue down, we get some of the statistics about what's going on, the amount of memory that it thinks it can compress and is available. So I've just started my new improved workload generator to keep my CPU and memory busy. And we can see down here in Topaz Nmon we use up nearly all the memory. This is the amount left on the free list. It's less than 1% over here. And we can see some paging going on here in and out of the system every now and again, so we know we've got the memory pretty well all used up. We can actually see SMT running quite nicely here. It's decided to run this number of compute cycles. It's going to use 2 CPUs, so it's using the first thread of the first CPU and the first thread of the second CPU. If it had more work coming in, it would go to the third CPU and then the fourth CPU. If there's yet more work, then it would start scheduling time on the SMT threads on the processor. So I'm going to run the AME pat command while our workload is running. The 1 means we're going to run it for 1 minute. Now, of course, that's not sensible in a practical situation. We should be knowing perhaps the busy hour of the day and running AME pat during that time to actually get a better analysis of the peaks and troughs of the memory use in a longer period of time. But my workload generator does a very consistent use of memory, and so we can measure it for just a short time for illustration purposes. I'll cut some time out of the movie. We'll come back when this is done. So at the end it produces a report. Let's go back up to the top of this report. Here we go. This is the stats we had a look at of the configuration of the machine. It then has some usage of the memory in here. File system very low. I'm not doing much with that. And how much CPU time it's taking. Then we get the more interesting part of the report, the compression ratio up here at just over 2. Then we have the report here saying, okay, if we ran it as an expansion factor of 1 and 1 gigabyte of memory, then this is the current config. We could take the memory down to 896 and boost the compression factor, and that would take 0.2 of a CPU. We could take more memory out, make the compression factor bigger, and that will be taking half a CPU to maintain us at that. And then it makes in a more wordy form a recommendation that this last line is what it would recommend us to do. It considers half a CPU as good use to save you 1/4 of a gigabyte of memory, but you'll have to make up your own mind in that. Well, that's the first way of using AME, where we want to reduce the memory inside a logical partition to free it up for other uses. Now we're asking it, I want this logical partition to have 1.5 gigabytes of memory. What expansion factor and how much real memory do I have to give it so that it thinks it has 1.5 gigabytes? So let's run that now. So here's the report. Here's the target, 1.5 gigabytes. Given the current workload, and it's worked out a compression ratio of roughly 2. So it says, well, if you give it 1.5 gigabytes of memory, it's no brainer. You could alternatively give it 1 gigabyte of memory and expansion factor of 1.5, and that will cost you 1.46 CPUs in time, compressing and uncompressing as you go. You might say that's a bit high, but perhaps we could justify giving it 1 1/8 of a gigabyte, a ratio of 1.3, and that's only using 0.19 of a CPU. So let's try that. We'll go to our partition, we'll do a dynamic memory add, and we'll change this ratio to 1.5, leaving it with the 1 gigabyte of memory, and it will be thinking it has 1.5 gig. All done. Now as the workload builds up, we'll use the lparstat -c. We can see it starting off 0 here and the workload building up. Initially it goes initializing all the memory it's got, and then it will steady down to only updating about 100,000 pages a second. So initially it's very busy here. If we look at the %X CPU, this is the compression CPU time being used. Here we go, we're starting to use it, so we've actually filled up all the memory, and now the compressions has to kick in to keep freeing up a bit of memory for us. So it comes and goes over time depending on the demand for those memory pages. Now it looks like we've reached a steady state of some compression going on as it touches particular pages that have been compressed, and they have to be pulled back out into real memory for real access. So here we are using Topaz Enmon, and the machine here now thinks it has 1.5 gigabytes of memory. We know in fact that's not true, and you can see down here the paging in and out has gone down. We're not actually doing disk I/O. Doing some scans in here. This is probably AME coming in looking for some pages now and again. So let's have a look at the Topaz command. We now have some more data down here for the AME data. The T memory, that's the true memory, real memory actually there, is 1 gigabyte, and the C memory, that's the compressed memory that's inside the true memory, 75 megabytes is being used for the compressed cache. And at the bottom we have the compressed in and compressed out paging in and out of the compressed cache. Above that we have the expansion factor, we have the target and the actual, and we can see we're actually hitting the target at the moment. We're not struggling to do the compression. That's active memory expansion. I hope you've seen that it's quite easy to set up. Unlike AMS, where we have to go and set things up on the VIO server and logical partitions have to cooperate, AME only involves a particular logical partition at a time. It also though requires AIX6. It doesn't work with the older versions, and you need a Power 7 machine to set it up.